The general things I see for some of you, units, okay? Some of you left out units. You had a long calculation, not a single unit in it. I took 3 points off out of 10. Okay, the units are just as important as the numbers, okay? So you must put them in there. If I don't see the units. Also, show all work. Now when it says convert this to powers of 10, I think 14 billion to a power of 10, well, there's no real work for that one. For the one where it said how many significant figures are there in each one of these, there's no work there. But otherwise, I want to see how you got the result. For some of you, when you were converting from years to seconds or something, you had a conversion factor, I don't know, it was 31, I don't know how many seconds per year. I know the hell you don't know that up here. I wanted to see 365 days in a year, 24 hours in a day, 3,600 seconds in an hour, or the individual ones. Because you may get a problem like that on an exam and I will not give you that conversion. I expect you to know the days in a year, hours in a day, seconds in a minute, and so on and so forth. But I will not tell you how many seconds there are in a year. So I took off if you used that conversion factor because you didn't show where it came from. I want to see your work. Units go in, units go out. Okay. A couple of you used the forbidden, I don't want to see that kind of crap. I want 6/3 like that. The reason is simple. It's not clear what is the denominator. Some people carry this to the point where it's almost a vertical bar. Now you can't tell what units are canceling. When you haven't firmly got an upper and a lower part of the fraction, you cannot see what is truly canceling out. Yes?
Is it okay if you use the slash when you're doing units, like if it's centimeters per second?
No. No, I don't want centimeters per hour. Nope, because the units are treated just like the numbers and cancel and multiply just like the numbers. Okay? And so you must be careful there. All right? Another thing is units, an hour. There's one that says multiply these two numbers, paying attention to number of significant figures and the units. An hour times an hour is an hour squared. A meter times a meter is a meter squared. A meter times a meter times a meter divided by a meter is a square meter, and so forth. You treat the units with the same reverence that you treat the numbers. And on the all or nones, I think I've got the quiz today. On the all or nones, if you have one little thing wrong, it will get marked wrong. The all or none, if everything isn't like it should be, it's wrong. So you got to pay attention to that. Somewhere here, I hope I have the quiz. I may have to run downstairs somewhere. Yeah, like I say, I don't know what happened to the quiz. I knew I'd forget something. The paperwork is just intractable. I almost can't deal with the paperwork. With quizzes and everything else, it's just almost too much. I can't even imagine doing this online. So I'll just have to run down and get the quiz when it comes to that time. Okay, well, let's move forward anyway. And let us see, these are all old. Also, tutoring is available. If you contact Colin, tutoring for algebra and tutoring for general physics and so forth is available. So you can check them out if you want to find tutoring. If I don't know, I haven't got the quizzes with me. All right. Well, where we are at is constant acceleration. And this is going to be an important foundation for the next chapter. And what I want to do today is talk about how you solve problems with constant acceleration. Now, last class I mentioned that there are 4 equations. So if you have constant acceleration, which also includes if the acceleration is 0. You just put 0 in these equations wherever you see an A, and you get the equations for 0 acceleration. Okay? There are 4 equations that you must be able to use. Not necessarily in the order of importance. The final velocity is the initial velocity plus the acceleration times the time. The final velocity squared is the initial velocity squared plus 2 times the acceleration times the change in position. The average velocity is the sum of the initial and final velocities over 2. Notice this does not contain the acceleration. It makes no difference what the acceleration is. It can be 0, it can be anything, as long as it's constant. If it's not constant, don't try and use these. Don't try and use them. We're going to see, though, that there are plenty of situations in nature where the acceleration is constant, and that's why we're worried about it. Another one, the final position is the initial position plus the initial velocity times the time plus 1/2 the acceleration times the square of the time. These are the equations that apply, and then there's a 5th equation, which is always true, which is very useful. So even if the acceleration isn't constant, this is always true, and that is the change in position over the elapsed time is equal to the average velocity. Notice there are 2 ways to calculate the average velocity. This one is true if the acceleration is constant. This one is always true. When doing any problems involving constant acceleration, step 1 of doing the problem is writing this down. Have it on a separate piece of paper if you want, but write all of these equations down so they are staring you in the face. Then you set up the problem and you come back to these and you try to figure out which ones might be useful. That's another problem that students will have, is how do I know which equation to use? The answer is, this is not an equation, this one right here for instance. It is a relationship. It has VF, VI, A, and delta X. If you know any 3 of those quantities, you can solve it algebraically for the 4th. This one here, x final, x initial, 1, 2, 3, 4. 5 different variables in that. If you know 4 of those variables, then you can invert the equation using algebra and find the other one. So this is actually equivalent to 5 different equations, 3 different equations, and so forth. A powerful technique is setting up the problem, then you go and check off the things that you know, looking for an equation that contains only one unknown variable. And even if you're not asked for that, you can still find it, because once you find that, you might be able to find what you were asked for. So you got to have these in front of you. Now you have to know how to use them. When it comes time to do an exam, they'll be provided, but you have to know what to do with them. Okay? So let us look at a couple of problems here and see. Let's do example 2-7. Excellent problem. And also, there are multiple ways to do problems. There are several ways you can do many problems. Sometimes they're easier, sometimes one is harder. Sometimes they're about the same. Okay? There are multiple ways. Okay? Now this one I call the airplane problem. You've got an airport for small planes, and a plane must reach a speed of 27.8 meters per second. A plane must be going 27.8 meters per second. See how I wrote those units? I didn't use that slash thing. Meters over seconds. Okay? If it's going less than that, it's going to crash. Okay, it'll stall, it will crash. All right? And we are told that this plane can accelerate at best at 2 meters per second squared. Now I'm not going to worry about significant figures here, okay? You can be a little loose with significant figures unless it's a problem where I say be specific about significant figures. Then I worry about it. But I don't want to see 6 digits in an answer. That's rubbish, okay? Now, here's the question, okay? If the runway is 150 meters long, can it reach this speed? If the runway is 150 meters long? Did I say it right? Don't trust your instructor, okay? Can it reach that speed? Okay? Step 1, you draw a picture. Okay? Now, we're assuming that our airplane is starting at what speed? 0. It's implicit here, but you still have to realize that V initial is 0 meters per second. We need to choose a coordinate system, so I'm going to choose to the right being positive, and I'm going to put it at the location of the plane before it kicks on the engine. By doing that, what I have implicitly done is I have said that X initial is 0 meters. By putting the coordinate system there, I made the initial position 0 meters. 0 is very convenient. It's great, like I say, unless it's your bank account. Okay? But it's also great if it's what you owe anybody. It's a great figure to have if you don't know anybody. All right, here is the end of the runway, and we are told that the runway is 150 meters long. So what you have to do here is you draw the picture, but then you have to translate the statements into mathematical statements. When we put X initial at the beginning at 0, and we're told that this is 150 meters long, what variable are we told? What is X final? 150 meters. See? X final is 150 meters. We're told that X final is 150 meters long. Okay? So the problem that we can ask is, we are told the acceleration is 2 meters per second squared. We're going to assume that you slam on, the plane slams on the engine, and it immediately starts accelerating at 2 meters per second squared. It continues the entire time. What we need to know then is, if it accelerates at 2 meters per second squared, how fast is it going when it has traveled 150 meters? If that is less than 27.8 meters per second, we are in trouble. If it's more than 27.8 meters per second, it's okay. This is a real life situation. I mean, they have to plan aircraft carriers. They know what the planes can accelerate at and so on and so forth. Okay? All right, what you can do, what I suggest you do is you make a list of what you want and what you've got and what you want. What we've got is x initial, we've got x final, we've got A, we've got V initial, we want a V final, okay? And what you do then is once you know what you've got, go over to the equations and put a check mark above those variables that you know. So, watch. We have V initial, we have A. Do we have T? No. Well, we can't solve that because we've got two unknowns. We got V initial, we've got A. Do we have delta X? Ah! We have X final and X initial. So here's a problem within a problem. They didn't ask us what is delta X, but we can find it. Delta X it's not one of those, but delta X we can find. Delta X is X final minus X initial is 150 meters minus 0 meters is 150 meters. So we have delta X as well. See, once you find something, you put it in the got column. Well, look at that. We know V initial, we got A, we got delta X. We don't even have to solve this. We just have to plug it in and then take the square root, right? Boom. Boom. So, once you figure out the equation you're going to use, write it down for me and write it down for yourself. Down here, Vf squared is V initial squared plus 2A delta X. Now we can plug and chug. V initial is 0. Okay. Why did I put the 0 in there? Because it's the right thing to do. Because it tells me that I thought about what the plane was doing initially and it was doing 0. Mathematically, this is optional, but I'm putting it in. Plus 2 times A, 2 meters per second squared, times delta X is 150 meters. Get your calculators out. And so it's 2 times 2 times 150. I got 600. And the units here are meters squared per second squared. I can now take the square root of both sides. If I take the square root of both sides, technically I get a plus or minus, as I mentioned in the algebra video, and I just hit shift there and I get 24.5 meters per second. Now since it's going to the right, I take that one out. It could be plus or minus, but the setup of the problem says it's going to the right, so we take the positive. Can it take off? Can it take off? No, it cannot take off. It cannot take off. It cannot take off. All right? So the next part of the problem is, all right, if we can't change the acceleration, and we got to get off, what do we have to change here? The length of the runway. Now you can't do that in real life, But if they're building an airfield, they say, well, how long does the carrier have to be so that this thing can take off? First of all, any questions on what I've done so far? Now, if I want to say how long should, so it can't take off. Can't take off. So how do we figure out how long it has to be? We simply come back up here and we say, now watch, if we change this and we say, suppose it's going 27.8 meters per second, and instead I say, how long does the runway have to be? Okay? How long does the runway have to be? Okay? Well, this equation still applies. What we're asking here is, what is delta x? Delta x is x final minus x initial, which is equal to x final. In this case, because x initial is 0. So I say delta x, what is delta x, given the situation? The only thing that changes is the last part of the problem. If we come over here, we will find, for this problem, that we have that we know everything except delta x. So what you do, listen carefully, is you do not start plugging numbers in. Instead, you solve it algebraically first for the unknown, and then you put numbers in. Get out of this old habit of trying to put numbers in and work with the numbers. Now you write it down. Let's write it over here so we have a little more room. So we determine that Vf squared is Vi squared plus 2a delta x. Who can tell me? I want to solve for delta x. What can I do? Anybody? First name?
John.
John, what do I do?
Well, you plug in the 27.8.
No. What do I do algebraically to solve this for delta x? Anybody?
The first thing would be to subtract the
V initial from both sides. Speak real loud too. Yes, subtract V initial squared from both sides. You'll see why. It gets me along the road that I want to get to. It simplifies this side and gets me closer to getting this by itself. Now what do I do? Yes?
divide by 2a.
Yes, ma'am. First name again?
Mel.
Mel. Ah, you go. Okay, Mel. Yes, Mel. So, if I divide and do it as a separate step, don't worry about taking in a little bit extra paper. We get that Vf squared. I've got to get a new marker. This stinks. Let's see if this blue one. So I get Vf squared minus Vi squared all over 2a is delta x. There is the equation that applies to this situation. What's V initial? 0. So I get that delta x is Vf squared over twice the acceleration is 27.8. Now watch how I do this. Meters per second, all squared, divided by 2. The acceleration is 2 meters per second squared. It's right there. And when you divide by units, you reciprocate and multiply. When you divide by units, you reciprocate the units and multiply. So this is seconds squared per meter. Take your calculators and you take 27.8 squared divided by 4 is 193. And watch how the units work out. This is a meter squared per second squared. Meter squared per second squared times second squared per meter. The seconds cancel, one of the meters cancel, and we are left with 193 meters. We have 193 meters. Now, an easier way to do this problem, what I would have done, because I can see ahead, if they said, can the plane take off, I would have done this problem first and said, well, it's got to go 193 meters to do it. It's only got 150. No, it can't take off. And I just figured out automatically that it needs 193 meters to do that. Write down all of the equations and start to go through them after you've set up the problem, figuring out what you've got and figuring out what equations you can actually find. Okay? Let's do another one here. Are there any questions? Yes,
So,
John.
you want us to first find the equation that it fits for, and then you want us to show...
I want you to do this. And then, once you've got this equation, then you put the numbers in.
Will we lose points if we don't, like, if we miss one step?
See again now?
If we miss, like, one of those steps?
I'd rather see all the steps of this case.
Okay.
I'm looking, I wish you could see my face there. I'd rather, you're not good enough yet, I think, to skip on all the steps. Show all the steps. Practice the algebra. Practice the algebra. Because you're likely to make a mistake. You're likely to make a mistake. Okay? Alright? But notice once I get here, I just say, well, that's 0, so that gives me this one. And then, boom, I have the answer. Okay? Alright, let me try another one here. Let us do, the acceleration of a car. This is example 2-8. Any other questions, John? Any other questions? Yes?
Yeah, with the second equation that we did when you got 193.
Yes.
Why did you, like, what made you have to do the first equation before doing that one? Like, don't you have all the information to do the second equation? Or am I missing something?
Which one are you talking about
Like
here?
the second equation.
When you're talking about the second equation, which one are you talking? This one right here?
Yeah, V initial plus V, I guess, final. My mind to it. The one below.
Here?
Yeah.
Yeah.
Yep.
You have to show where this came from. You can't just pull this out of a hat. You can't go into the book. I don't want you to go into the book, find a problem, and yank this out. I want you to do this, this, and this, and show that this applies to this problem. I want you to be able to develop your own equation for each different problem that comes along.
Okay.
You might be able to hunt through the text and say, I found this equation right here, and just plug it in and get the answer. Wrong, wrong, wrong. That means you don't understand the problem, and I want to see understanding. You won't be able to do a problem if that book isn't in front of you. See what I'm saying? And that equation right there is not going to be on the equation sheet for an exam. These will. This will not. You need to be able to manipulate the equations to get the equation you need. That's part of the course. Okay? The ability to manipulate and solve problems to get what you need based on the fundamental equations. Let's look at this other one. At least we can start it up here, because I'm going to have to run down and get those quizzes. I don't know where they wound up. I thought I had them all ready to go, but turns out not sure where they're at, but we'll get something here. Okay, let's see. Let's do 2/8. Let's do 2/8. In example 2-8, how long does it take a car to cross a 30-meter intersection after the light turns green if it accelerates from rest at 2 meters per second squared? So we can say car accelerates from rest across 30 meter, did I say 30 meters? 30 meter Y intersection at 2 meters per second squared. Car oxide for rest across 30 meter wide intersection at 2 meters per second squared. Now, they say how long, but I will warn you, I may have an exam question that doesn't ask you for a specific thing. I might say find everything you can. What is another possible thing you could find here? If I draw the picture, here's the car, here it is afterwards. It's not going at all. The intersection is 30 meters wide and the acceleration is 2 meters per second squared. All right? What else could I ask? Yes?
Maybe velocity.
Yeah, doesn't this look like the plane problem? In fact, I can't believe that the book actually used the same acceleration. Okay? Yeah, how fast is it going over here? How fast is it going? See? I might say, find everything you can. I'm not going to tell you to find anything specific. Figure out what you can. Now, I think what I'm going to do here, because we've got the quiz coming up, is if you come over here, what is it asking for? The time, right? Well, can we use this one? Not yet. Why? We don't have this. We don't have that. Can we use this one? We know A, we know delta x, we know V initial. Can we find this? Yes, we can. Is that what's asked for? No, but we can do that. What about this one? X initial, X final, we got that. We got V initial, we got A. This would tell us the time. Okay, this would tell us the time. You could use this one to go right after the time. Okay, you could, but this one is certainly easier, I think. All right? There are two ways to solve this, okay? What I'm going to do is I'm going to point out the ways to solve this, and we'll come back to this next class. One way to solve this, now watch, is to find the final velocity. Take this just like we did and find the final velocity. If you know the final velocity, once you got the final velocity, can you find anything with this? Yeah, you can find the average velocity. You can find this and put it in here and find this. And if you got this, you can come down here and you can find the time. It turns out that's a lot easier than going right after this, because what kind of an equation is this going to be? What's this square mean it's going to be? It's a quadratic equation. So the real way to do this is to solve this one first, then take that answer and put it in here to find this, and then put that in here, and you find that delta t is delta x over V bar. So that the elapsed time can be obtained from this. And it turns out that two-step process or three-step process is probably easier than going after it here. Yes?
Instead of using the second one, like still doing the second step, couldn't we use the first one, do the first step, and then
You don't.
do the top one?
Say it again. Good man. Go ahead.
So couldn't we just do the
He said, it sounds like this up here, but I'll say it clearly. You are absolutely right. If you find V final, you can go in here and find the time. That's yet another way to do it. There's at least 3 ways to find the time in this problem. But 2 of them say find the final velocity first and then use a couple of the other equations. You could go straight for this one, but it turns out that one will probably be fairly hard. Now stand by.